Hello and welcome to another slide video from the Cornish Radio Amateur Club. And today this is a foundation series, a part of the foundation series leading to the foundation license. And today we're looking at frequency and wavelength. Now you will recall that the technical basics part of the foundation syllabus addresses the basics only. And we've looked at the items there from A to E, and so today we're looking at frequencies and wavelengths. But if you haven't covered those videos, A to E, I recommend you do so before looking at this video. Indeed, it's probably best to attack these in alphabetical order. Let's have a look at what the syllabus says about this. So 3C1 says, recall the unit of frequency and understand the meaning of the abbreviations RF, that's radio frequency, and AF, that's audio frequency. So identify the graphic representation of a sine wave and recall that sine waves are produced by oscillators. So continuing on, recall that the range of frequencies for normal hearing is 100 Hz to 15 kHz. Recall the range of frequencies for audio communication is 300 to 3 kHz. So we limit what we send to air for practical reasons. Recall the frequency bands for HF, VHF and UHF radio signals. And as I say, this is just the basics, but if you want to have more information, you can look at the background video radio waves, which goes into more detail as it gives a more in-depth view of transverse electromagnetic waves and is useful for general understanding if you intend to go on to the advanced course and the intermediate course to the advanced course. So the foundation license distinguishes between RF, radio frequencies, and AF, audio frequencies, by the value of the frequency. So those are the things that you need to learn for the examination. If you dig a little bit deeper, and this isn't required for the foundation exam, you will see that there is a fundamental difference between radio waves and sound waves other than the frequency which is used. Sound waves are longitudinal compressions of a medium, usually air. So if we apply an AC signal to an input of a speaker there, it will produce sound waves as the cone vibrates. So that's areas of compressed air travelling out longitudinally along the wave from the speaker. And so a medium is required. Sound waves must travel in either a gas, a liquid or a solid. Sound waves will not travel in a vacuum. Radio waves are electromagnetic waves and can travel in a vacuum. And if we replace our speaker with a transmitter and an antenna and apply a higher frequency radio signal, we get an electromagnetic wave coming out. So this isn't compressions of a medium. This is an electric field and magnetic field travelling out from the antenna at the speed of light. And this is a fundamental difference between the waves. Now, for the foundation license, we learn the frequencies of audio signals, and then anything higher we assume then it becomes a radio signal. And for practical purposes this is absolutely true, because to produce electromagnetic waves at the low frequencies for audio transmission is, let me say, extremely difficult. They do exist and they do occur naturally, and they have been produced, but from a practical point of view, the differentiator between audio and radio is frequency. But this is a little bit of extra background to say, well, actually the nature of the wave itself is different. So there we are. That you do not need to know, the difference between sound waves and radio waves other than frequency. You do not need to know for the foundation course, so learn those frequencies. So sound waves are audio frequencies, we've said that, and the values in the syllabus are 100 Hz to 15 kilohertz, and that is the sound of the average human being able to hear. Now, here I'm trying to produce a signal near the top end. I tried to produce a 15 kilohertz signal, but couldn't hear it from my speakers. I don't know if it's my speakers or my ears. So I've produced a 10 kilohertz signal, which I can hear on my computer. You may or may not be able to hear it on your computer. So here it is. This is 10 kilohertz. And at the bottom end then, similarly, I couldn't really hear 100 Hertz. I could vaguely detect a hum, but I suspect by the time it's been made into a video, it would be undetectable. So I doubled the frequency, so here's 200 Hertz. So that gives you a feel for the range of frequencies, 100 to 15 kilohertz, that are part of the AF range. Another syllabus item says you need to learn the graphic representation of a sine wave, and there it is on the screen. And if you wish to look at the background series of videos for further study, I would recommend that. And the sine wave is an example of simple harmonic motion, which occurs a lot in nature. So another item that we need to do, we need to recall the unit of frequency and understand the meaning of the abbreviations RF and AF. So RF being radio frequency and AF being audio frequency. We've learnt the range of frequencies for audio frequencies, 100 Hz to 15 kilohertz, and we've learnt the range that we normally send to air, only 300 Hz to 3000 Hz. Or 300 Hz to 3 kilohertz. And we do that for practical reasons to limit the bandwidth of the signal that we send. That's so we don't occupy too much RF spectrum unnecessarily. So radio frequency, we said, are electromagnetic vibrations. Audio frequencies, vibrations in air, liquid or solid. Normal hearing 100 Hz to 15 kilohertz. And the range for spoken audio communication, 300 Hz to 3 kilohertz. So those are facts that you need to have at your fingertips in the examination. Let's go back and look at some radio frequencies. Well, understand that frequency bands are allocated for particular use. This is an example of the sheet you will have in the examination. It's designated as EX301. If you like, it's the handout that you can use to answer some of the questions. In fact, you will need, because you won't memorize, nobody would, all of the facts on that handout. And this is a subset of allocated frequency bands. And you can see there that people share, or different users share, the RF spectrum. And this is a matter of national and international coordination to make sure that people do not interfere unduly with each other. And within those allocations, you can see they're highlighted in red, some allocations for amateur and amateur satellite. So there are many users of the RF spectrum. They are broadly divided up, I suppose, into one-way communication or broadcast, where people consume services, and two-way communications, where people speak both ways, for duplex, which means both-way conversations. So there in yellow are some of the broadcast services. You can see radios, TVs, and the radios pick up signals on long wave, AM, shortwave, FM and TV. Now, in normal speech, we alternately talk about wavelength, frequency, and the type of modulation. So when we say long wave, we're talking about a signal with a low frequency which has a long wave. When we talk about AM, we're talking about a signal which has amplitude modulation. And it doesn't really indicate on what frequency it is, but we come to know roughly where in the band we will find AM, and we all know what we mean about it. Short wave, similarly, means higher frequencies with shorter wavelength. FM talks about frequency modulation, and TV talks about the type of service. So colloquially, when we're talking casually, all of the terms get mixed up, but somehow we seem to know what we're talking about. Other users are there, of course. Aircraft, aeronautical, use it for ground to air and air to ground. In other words, aircraft speaking with a tower. Mobile communications providers provide links for full duplex, full both-way conversations between the handheld mobile and the radio base stations that you see located on dotted around the country on tops of hills or buildings, and less visible microwave links carrying signals up and down the country, radar for tracking the movement of planes, and also satellite, ground to satellite and satellite to ground dishes such as Goonhilly or Madley, I think in Cheshire. So many users of the RF spectrum, and if we were to map them, if you like, over the overall spectrum, they would look something like that, occupying chunks of spectrum. Now the bar on the bottom, these are the ITU designations. Don't worry, you don't need to learn all of these, from the very low frequency to the extremely high frequency. So starting at the bottom on the left, it's very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, and extremely high frequency. And above it, there you can see the band edges for these designations. So for example, we can say that HF is from 3 MHz to 30 MHz, and VHF is from 30 MHz to 300 MHz. Now, apart from the allocations to many services out there, dotted in between them are allocations for amateurs, usually on an exclusive basis, but sometimes on a shared basis, and we'll talk about that a bit more. Now, the lowest allocations in the UK are 135 kHz, and the highest are around 250 GHz. But there in green, HF, VHF, and UHF are the ones we need to concern ourselves with for the foundation license, or the bands within which we have allocations that we need to concern ourselves. Now, 135 kHz means very, very long antennas, and it's quite a practical challenge for amateurs to do that. So perhaps not too many people brave enough to attempt communication at 135 kHz. And at 250 gigahertz, also significant problems in practical difficulties, should I say, in producing frequencies in that range, and the range of transmission is very, very low because you get atmospheric attenuation at those SHF and EHF frequencies. So if I draw some of the amateur allocations, and this is by no means all of them, you can see quite a few of them are clumped around HF, VHF, and UHF. And anecdotally, I would say that something like 80% of amateurs operate within the area of the blue box there. And so HF, VHF, and UHF are the main bands for, if you like, your average Joe operator, and that's where you'll find most of the activity. Some intrepid amateurs also operate on frequencies about 1240 megahertz as well, and 23 centimeter wavelength. But basically speaking, that is why the foundation examination concentrates on learning the frequency ranges for HF, VHF and UHF. And so you should recall that HF is from 3 to 30 megahertz, VHF is from 30 to 300, and UHF is from 300 to 3 gigahertz or 3000 megahertz. So there we have it. That's what you need to memorize. Now, to see what are the amateur allocations within all of these frequencies, you will see as part of your license something called the foundation license parameters. And on this then we have 4 columns: the frequencies of the top and the bottom of the band, the status of the allocation in the UK, and this is basically a comment field where it's saying whether it's primary, in other words, amateurs are the main users, secondary, where amateurs are, if you like, the secondary users, and whether or not it's shared, in other words, whether it's exclusive to amateurs or shared with other users. The third column then says status of allocations in the UK to the amateur satellite service. This is saying, are these frequencies in use for amateur satellites, and on what basis? And then it says the maximum peak envelope power level in watts, and then in brackets it says and dB relative to 1 watt. So you don't have to worry about dBs for the foundation course. This is simply another measure of power. So ignore what's in the brackets, except that you may need to reproduce it. Just simply look it up and reproduce it in a multiple choice question. But other than that, you don't need to have any understanding of what a dB is, a decibel. So having a look at that, let's have a look at an example from the first column. So on the first column then, this is part of some allocations. This is part of top band, which is starts, so you can see 2 rows above at 1.81 and goes up to 2 megahertz. And the band then is divided into 3 chunks. The lower band, in other words 2 rows up, is primary, available on the basis of non-interference to other services outside the UK. And then just above it, 1.83 to 1.85, is primary. In other words, you don't have to worry about non-interference. And then the last bit, secondary, available on the basis of non-interference to other services inside or outside the UK. So you've got a single band there, or top band as we consider it, and it's divided into 3 chunks. And we need to understand that we use each of those chunks on a different basis. Now, the most powerful chunk for us, I suppose, is 1.83 to 1.85. In other words, it's exclusive to us. But on either side, we're bracketed by different conditions. And the multiple choice questions in the examination will ask you to reproduce, if you like. It'll give you a frequency. It'll say in the back you are transmitting on a frequency of 1.815 megahertz. On what basis can you use this? Is it A, primary, available to the basis of non-interference to services outside the UK? Is it primary, or is it secondary, etc.? So you'll need to be able to answer questions based on looking up the frequency there. Then having a look at another one here. Okay, and we've just talked a bit about this. that band there says it's secondary, available on the basis of non-interference to other services inside or outside the UK. This basically means you need to defer to everybody else. But if you do find a frequency that's free, go ahead and use it. Here we're looking at the satellite allocations, and here the frequency band 14 to 14.25. You're able to use that to communicate with satellites if you can find a satellite operating on that band on a primary basis. So Earth to space, that is a primary frequency. And on the right hand column there, this is the peak envelope power. You don't have to worry about the definition of that, but the PEP, the peak envelope power in watts, that you're allowed to emit. Now, in the exam, they differentiate quite clearly between 1 watt ERP, which is effective radiated power, and 1 watt. So the question might be, for this frequency band, 0.137 to 0.1378, the question might be, what is the maximum power you're allowed to radiate? Is it 1 watt, 1 watt ERP, 10 watts or 15 watts? Well, the answer is 1 watt ERP. So look carefully in that column to see if the ERP, effective radiated power, is mentioned. Now, if you look in the book Foundation, you will see that effective radiated power means the power going to the antenna times the linear gain of the antenna. So we'll talk a little bit about that as we go on in these videos, but that is something to look out for. If we scroll down, we can see, for example, here that on 51 to 52, it's available on a basis of non-interference, just as an example. And if we look at this one, this comes up in questions. 431 to 432 megahertz is secondary, but it's not available for use within a 100-kilometre radius of Charing Cross, London. So that sometimes is used to form a question. You are 40 miles from the centre of London. Sorry, not miles, kilometres. You are 40 kilometres from the centre of London. Are you allowed to use 431 to 432 megahertz? The answer is no, because you're within 100 kilometres of Charing Cross. So once again, the frequencies to memorise for the exam: 3 to 30 megahertz for HF, 30 to 300 for VHF, and 300 to 3000 for UHF. In a way, you've only got to remember the 3 to 30 because the other ones just simply build from that band edge up in with multiples of 10. So that's quite easy to remember. You do need to remember that 3 gigahertz is the same as 3000 megahertz. So I've shown it as in both ways on the screen. So those are the 3 bands there. Those are the frequencies of all of the bands, and we can look at the wavelength now of the bands. You can see the practical problems of producing antenna which need to be something like a half-wave dipole or something at the very low frequencies. So if you were to try and produce an electromagnetic signal at 3 kilohertz, you would need a 50-kilometer antenna, and that will be very difficult. At 30 kilohertz, you still need a 10-kilometer antenna, and you can see that it's quite difficult to produce antennas at 300 gigahertz because they're only 1 millimeter long, or for a half-wave dipole it would be at half a millimeter. So different technologies are required. So looking at the antenna wavelengths, then the bottom end of the HF band is 100 meters, and the top end of the UHF band is 10 centimeters. So those are the wavelengths over which we typically operate, from about 100 meters to about 10 centimeters. So quite a range. So you can see then, as you increase frequency, then the wavelength decreases, and we've looked at that in other videos. Now, converting between frequency and wavelength, you can either use the formula V equals F lambda, which is not required for the foundation course, or you can use this chart which you're given in the handout EX301, and you will have this chart available to you in the examination itself. So let's have a look at an example of this. Then we could say, what is the wavelength of a radio signal with a frequency of 30 megahertz? So we draw up a line from 30 megahertz on the bottom axis there, where it says frequency megahertz, until it intersects with the graph. Then we draw a line horizontally, and we get the answer 10 meters. Now, if you're feeling intrepid and want to go on beyond foundation, you might wish to use the mathematical way of doing it, where lambda, which is the representation of wavelength, is equal to velocity over frequency, v over f, equals 3 times 10 to the 8th over 3 times 10 to the 6th. 3 times 10 to the 8th is the speed of light, and 30 times 10 to the 6th is 30 megahertz. We've gone back to the base units in each of these cases, and that also gives 10 meters. And I've put a square around it because that absolutely is not required for the exam. You simply need to be able to draw up on the graph from the frequency to the wavelength. So similarly, you need to be able to do it the other way. What is the frequency of a radio signal with a wavelength of 20 meters? Well, we've been given the wavelength, so we start on the wavelength axis, we draw horizontally until we intersect with the graph, and then vertically down. And the answer then is 15 megahertz. Now you may say, well, I can see that it's between 10 and 20 megahertz, but I can't determine that it's 14, 15, 16 megahertz or whatever. If you're given these types of questions in the exam, remember it is multiple choice, and the spacing of the alternatives will be such that it's clear which is the right answer. So, a final pass through the syllabus. Let's have a look. Recall the unit of frequency and understand the meaning of the abbreviations RF and H and AF, radio frequency and audio frequency. And the unit of frequency is the hertz, used to be called the cycles per second. Identify the graphic representation of a sine wave and recall that sine waves are produced by oscillators. Plenty of these videos have examples of sine waves. One of these early slides had the shape of a sine wave, and so that shouldn't present a problem. Recall the frequency of the main supply, 50 Hz. I think we probably all know this anyway. It's marked on consumer equipment, 230 volts or 240 volts AC, alternating current, 50 Hz. So that signal is changing between positive and negative as alternating current. So I think that's easy enough. So recall the range of frequencies for normal hearing, 100 Hz to 15 kHz. Now you'll need to remember that, 100 Hz, 15 kHz. Some people are able to hear higher frequencies, particularly when they're young, and lower frequencies. In this slideshow, I produced signals of 200 Hz and 10 kHz, just to give you a rough feel of what the frequencies might sound like. Recall the range of frequencies for audio communication, 300 Hz to 3 kHz. When we look at modulation in subsequent videos, and also in the intermediate and advanced course, we can see that the bandwidth, or the space we occupy on the RF spectrum, is dependent on how much information or how much bandwidth we want to transmit to air. So if we want to send music from, let's say, 100 Hz to 15 kHz, we will use a lot of RF bandwidth. But if we restrict the amount of frequencies to 300 to 3 kHz, we use less RF bandwidth. So it makes sense then for audio or spoken communication to limit the bandwidth that we send, or limit the range of frequencies that we send to the minimum, consistent with intelligible speech. And it's been determined over many years that 300 to 3 kHz is fine for the spoken word. If you try and play music and restrict the bandwidth to 300 to 3 kHz, it sounds tinny and unpleasant. You can still make it out, but it doesn't really sound correct. So that's the reason why we limit the bandwidth, and those figures you will have to learn: 300 and 3 kHz. Similarly, you'll have to remember that the HF band is from 3 to 30 MHz, and then the top of the VHF is 300, and the top of the UHF is 3000. It's fairly easy to remember, simply need to memorize those. So in summary then, this video has probably gone into a bit too much detail. It gives you a bit of background though, and you've got some figures there that you need to learn. Thank you very much from the Cornish Radio Amateur Club.